next part, I think it's just like high-level detail about matrix decomposition. We are not going to do any derivations here because that I think will take like just 1 or 2 lectures, and that's not the focus of this course. So we'll just skim over this and try to understand the intuition behind matrix decomposition. Okay, so before going there, let's try to understand the concept of linear independence. The mathematical definition says if we have set of vectors, in this case, starting from x1, x2, all the way up to xm, and if we say that these are linearly independent, so this condition should met. All right, so if we arrive at a situation where we take linear combination of all these vectors and it sums up to 0, then it should happen only when all the coefficients of these vectors starting from a1 to am all are 0. If they are not 0, then this will never happen. So that's like a mathematical condition to assume that all these vectors are linearly independent, which is fine, but let's try to understand like a more intuitive meaning. What does it mean by having linear independence? Okay, so if you look at like the coordinate system, let's say 2-dimensional space, then we can say that the axis of that coordinate system, x and y axis, they are perpendicular to each other, right? And they are linearly independent. Okay, so that's one simple example. So even if you extend that to 3-dimensional space, your 3 coordinate axes will be linearly independent of each other. And that's the whole reason we have 3 axes for 3-dimensional space, because we need at least like 3 dimensions, or you can say like 3 directions to define any point. We can't do that with less than 3. If you just have 2 axes, that will reduce to 2-dimensional space. All right. So if you move towards the other direction, let's say you use like 4 different axes to represent a 3-dimensional point, which is kind of axis. We don't need that. It means that one of the axes is actually a linear combination of the other 3 axes we have. So the minimal is like 3. Okay. So let's try to understand like from more vector examples here. So let's say we have a vector in this direction and we have another vector in the same direction. These are not linearly independent. And the reason is, if we have the, let's say the shorter vector, I can just scale it in that direction and get the second vector. Okay. So we can actually perform linear combination or scaling operation to get the second one. So that's why they are not linearly independent. And this is again the same example I discussed earlier. This is, let's say, a 2-dimensional coordinate system. Then we need 2 different axes, and these are perpendicular to each other. There is no way that you can define any point in this direction with the help from this axis over here. In whichever direction you go, it will not describe anything which is happening in this direction. All right. But this is another case. Again, this is 2-dimensional coordinate system. I understand it can be difficult like to visualize that in 2D space. This can also be interpreted as 3D, but it's not 3D. It's again 2D space. And this is like axis, x-axis. This is the y-axis. And this is just a vector in this direction, in the same plane. Now, we can say that this vector can be represented as a linear combination of this axis and this axis. And that's why it's not linearly independent. That's how the 2D coordinate system works. And if you move on to 3D system, in this case, we can see like this is 3D space, but I don't know how to show that in 2D plane. But all these are like perpendicular to each other, and these are linearly independent. And again, this is like showing 2 vectors again in 2D plane, but you can see that it's not 90 degree, it's at an angle. So again, these are not completely linearly independent because this vector has some component in this direction, which you can also say that is like the projection of this vector on this axis. Okay, so not completely independent. Now, why this is important? Yes, go ahead.
So I have a question. I'm sorry to interrupt you. So the linear independent means they're always perpendicular to each other. That's what it means. The vectors are always like perpendicular to each other. That's when they're linear independent. Is that the conclusion to make?
In 2-dimensional space, yes. But usually we work in high-dimensional space, so you can't say like perpendicular, right? You can say orthogonal or something like that.
Sure.
But for 2 or 3-dimensional, you can say that.
Okay.
Now, so that's like toy examples, but let's see like what's the real world interpretation of this. For example, if you have to perform, let's say, person identification, right, in biometrics, then for each individual, you might have different set of features. It could be like the facial features. It could be like height of the person. It could be hair color, weight of the person. So what's going to happen is like some of these features will be linearly independent, which means that one feature doesn't affect the other, right? So and that's the like real world relevance of understanding this linear independence, because it helps us in understanding like what's the bare minimal we need to, let's say, represent a person for person recognition. All right. So for example, I can give you another example from the same scenario. So you can have like your BMI, which is dependent on like height and weight, right? So in that sense, if you combine all those together, there might be something which is not linearly independent. So there might be some repetition. Okay, so that's the real world relevance. Now let's move on to like a very concrete example of where this play a very, very important role. And before that, let's talk about matrix factorization. And there are a lot of different ways how you can factorize your matrix, and singular value decomposition is one way. The idea here is if you have a matrix A, you can decompose this matrix in three different matrices. All right, so U, sigma, and V. A in this case is a M cross N matrix. So when we perform this SVD decomposition, these will be the dimensions of U, sigma, and V. So U will be M cross M, sigma will be M cross N, and this V is going to be N cross N. And both these matrices, U and V, are going to be unitary matrices, which means that their columns, in case of U, the columns is going to be of length unit, like whatever axis we have. Similarly, in case of V, it will be a unit vector. And in this case, sigma, it's a diagonal matrix, which means that all the off diagonal values of this matrix are going to be 0. Okay, so now let's try to understand like why that's important and what's the interpretation of such a decomposition. Now, given a matrix, when you perform this kind of decomposition, what will happen is sigma will have, as I said, like all the diagonal values, and those diagonal values actually are used as a scaling factor for all the columns which are present in U, and all these columns in U are actually unit vector, and they are linearly independent. Okay, so what will happen is if we multiply these two matrices, the columns in U will be scale using all the diagonal values. So they're kind of magnitude of when we try to perform the linear combination. All right. And so that will be scaling. And then the linear combination, the weights will come from like the rows of V. Okay. So what's happening here is if we decompose A into these three matrices, and if we use like full matrices U, sigma, and V, we will be able to reconstruct full A. But what if we try to trim these matrices? For example, in U, if we use like only some of the columns, all right? And again, we'll have to use like some of the corresponding values from sigma. So in this case, all these columns we are using, again, we will take linear combination and try to reconstruct A. Again, it will be like an approximation of A, but not exactly A. Okay, so let's try to understand like this when we try to decompose an image, because image, we can also represent that as a matrix, right? So let's say we have this this image over here, and the resolution is 256 cross 256. Now, if you go back to this formulation here, U will be a matrix which will have 256 rows and 256 columns. And you can say that it will have 256 different columns. And for each of those columns, we'll have 256 different values along the diagonal of sigma. And these are just like the weights which are going to be used when we perform linear combination of those. Now, what we can do is so one more point here, this scaling matrix, which is like sigma, these are kind of like, we call these eigenvalues, but let's not go there. These are kind of importance of the vectors we have found in U. So this is kind of in a decreasing order. The most important vector will be like on the top. So that will be like have the highest magnitude. Okay. And if we do that, let's say if we just select 20 of the columns from U, then still we are able to reconstruct this image. So you can see that like the principal components which were found like using that decomposition, we were able to actually find the very, very salient components of this image. And initially it had like 256 different vectors, but just using 20 is actually giving you this kind of reconstruction, which means that most of the information about this image was captured using those vectors which we extracted. And of course, if you keep increasing that, the quality will improve. There is some loss of information, but if you go to like all the way up to 85, you can see that it's like a very minor drop in terms of performance, right? When you compare to this. But in terms of like values you're using, it's pretty small compared to like 256. It's just 85. So it's just not numbers, right? Because those are matrices of 256 cross 256. So it's like a huge reduction in terms of memory which will be required to save this image. And this kind of technique was actually used when like the first image which was sent from moon to earth. So this PCA was used, matrix decomposition, and they sent like fewer principal components, and then the images were reconstructed. Because if you think about, if you have to send this whole image, the total number of values will be 256 cross 256. But if you perform this decomposition and let's say you only use 85 singular values, the number of values you are actually saving, it's drastically small, because your matrix U will be 85 cross 85. Again, sigma will have just 85 different values. And again, V will be compressed. So in terms of memory, it's a huge gain. Okay, so that's kind of one application where matrix factorization is used.